Hello my friends, in this video we are going uh, to model the induction motors, and last week we have already explored the basics of induction motor, and this is what we have done last week in the last video. We basically have a stator. Stator is the house of the induction motor, the the metal which supports the electromagnet, so-called poles. And the stator is powered by a three-phase electricity, like what is demonstrated here. So with these three-phase electricities, or polyphase AC electricities, we will end up with a rotating magnetic field. And this magnetic field will eventually drive the rotor to rotate as well. The rotor will rotate in the same direction as the direction of the rotating magnetic field, but at a much reduced velocities. Now take a look here. At the starting point, the motor will carry a lot of torque, and this torque is so-called start-up torque. So if you have a start-up torque, this means you also have a start-up EMF, because the torque is actually equals to the converted power, the power that has been converted into mechanical energy, divided by uh, the angular speed. Maybe you should write the speed in this manner. 2 pi nr, where nr is the angular speed in per minute. So in this case, we have to divide the bottom expression by 60. Okay, so this is the equation for the torque, and at this point, the power converter is not a constant. If it is a constant, then we will end up with a inverse relations between the torque and the angular speed. But it is not, according to what we have got from the last video. The torque is going to go down a little bit, and then as the speed speed up, the torque goes up as well until it reaches a maximum. And this maximum is so-called breakdown torque. So there must be something in the power converter. The converter power must be a function of the speed of the rotor. So today we are going to model the transformer, and at the end we will be able to use the models to derive the speed of to derive the torque speed relations of the induction motor. Now the motor itself has an array of electromagnets in the stator. And this array of electromagnets is not very much different from the primary of a transformer. And suppose Right now, right, we have a electromagnet in the status. So the status itself can be modeled as a primary of the transformer. Oh, and then how about the rotor? The rotor is driven into motion, and so this is the only difference between um, the rotor and the secondary of the transformer. Apart from that, the rotor is also electromagnetically induced. So basically, the nature of the rotor is not much different from the secondary of a transformer, with an exception that the rotor can rotate. The secondary of a transformer cannot rotate. So in this case, uh, let's write down. Let's start with the model of a transformer. And in a transformer, we have a primary and we have a core. And the primary here is XR, so R1 and JX1. And likewise, we have a core, and this core dissipates the magnetizing energy as well as the uh, as a heat. So the heat will be dissipated as well in the form of eddy current. And as I said before, um, the motor is not very much different from a transformer. So the status here is like that, right? So this is one phase of the induction machine. The induction machines might have polyphase, but we only need to take one phase. And if we modeled one phase properly, then uh, what we can get from the models will be applicable to the other phases. And the voltage per phase is V1. And like what I said before, it's just like the transformer. And then the transformer here has a secondary as well. The primary of the transformer is used to model the stator. Indeed, right, the stator is just a electromagnet. It's just an array of electromagnets. But the rotor itself is somewhat different. The rotor have low wire connections. So in this case, uh, you may have parasitic, but the parasitic is not the parasitic of copper winding. So in this case, what we can do is we can just immerse the rotor as the secondary of the transformer. And at the end of the modeling, we revert everything from the rotor, or so-called the secondary, to the primary. So in this case, whether we have wire connection in the rotor or not, it doesn't really matter. Now, The rotor itself is just a conceptual model. The rotor doesn't have any wire connection, but we can conceptualize this. We can conceptualize it as uh, as a real primary of the transformer. Sorry, as a real secondary of the transformer. So we assume it has a resistance and inductance. So now we have inductance. And this inductance is so-called JXR. R stands for the rotor. And then it has a resistance as well. And this resistance is R, R, R. Okay? And this R stands for resistance. The other small R stands for the rotor. And the transformer here is an ideal transformer. And we are now trying to use the skill we have from the chapter of transformer to, to build up a model for the induction motor. So there is no loss in this transformer because it is an ideal transformer. But we have a voltage built up in the secondary, and this voltage is so-called E ER. R stands for the rotor, and we also have a status voltage ES. Okay. Now, before going forward, we need to have some concept. And instead of dividing everything into equations, we are going to just memorize some concept. So first of all, the rotor will be rotating at a speed much less than the speed of the rotating magnetic field. The speed of the rotating magnetic field is so-called synchronous speed. Is so-called synchronous speed. And it is also so-called stator speed. Stator speed. And we normally denote it as NS. And there is a formula associated with this NS. 120 times F divided by P. F stands for the frequency. Frequency of the supply voltage. And P stands for the number of poles. So in this case, we have 1, 2, 3, 4, 5, 6, 6 poles. So P is 6 in this case. So we don't need this diagram anymore. The stator, which is the primary of the transformer, and the stator is going to experience a frequency F. Because the status itself is just a electromagnet, an array of electromagnets running at the supply voltage at frequency F. The rotor itself is somewhat uh, different. First of all, the rotor voltage is going to be, let's say, before going forward, right, we need to build up some concept first. The we have the formula for the synchronous speed, and the rotor will have its own speed, and the speed of the rotor, the angular speed of the rotor, and R is is much less than the uh, the synchronous speed. And usually the difference between the speed of the rotor and the speed of the rotating magnetic field can be related by a parameter so-called slip. And the slip is defined as ns divided. And because of this formula of slip, we also know that the the rotor speed is going uh, to be a function of the synchronous speed. And the formula, yeah, according to this slip equation, slip formula, then it is going to be ns, which is the synchronous speed, multiplied by bracket 1 minus s. And with this in mind, we also have another relations. Another one is uh, the the voltage of the rotor is going to be S times ER zero. ER zero is the rotor voltage at standstill. And now let's take a look in the rotor circuit. The rotor is rotating, but not as fast as the stator. The stator has a rotating magnetic field, which is running according to this formula. So it's actually the function of the frequency and the number of poles. But the rotor itself is running at a reduced speed, and because of the reduced speed, the rotor's frequency will be different. The rotor frequency will be equal to uh, F R equals to SF. The sleep times this frequency times the supply frequency. So this is something we have to memorize. Otherwise, there's no way to go forward. So now, right, before moving forward, let me just highlight the fact that the secondary of the transformer is going to be used to model the rotor. So we have a few formula here. The rotor frequency is SF. The rotor voltage is S times ER0, where ER0 stands for the voltage at standstill. And we also have the speed of the rotor. The speed of the rotor can be expressed as a function of the speed of the rotating magnetic field, as well as the slip. Okay? Now, take a look here. We have a circuit here. And as I said, the frequency of the status is F. But the frequency of the rotor is SF. You have two circuits here, one for the rotor and the other for the status. The status is running at frequency F, while the rotor is running at frequency SF. These two pieces are not running in the same frequencies. So if they are not at the same frequency, it is impossible to model them as a transformer. In a transformer, the primary and the secondaries are both in the same frequency. So what we need to do is to do some treatment. First of all, we have a voltage here. And we are going to consider the rotor individually. Initially, the rotor circuit is like this. ER, and then uh, XR, and then R. So this is the rotor, and it is running uh, at this frequency, SF. Again, so it can be related by Ohm's law. IR is equals to ER divided uh, by R. There's not much we can do from this equation apart from substituting the essential parameters here. According to here, the rotor voltage can be substituted with S E R0. It's not much useful. And according to here, right, the XR is 2 pi the frequency, right? The frequency is going to be different. The frequency of the rotor is F R, and then times the inductance, the actual inductance of the rotor. And this is so-called the induction of the reactant of the rotor. And but then, like according to the formula here, the rotor frequency is actually is actually SF. So the rotor frequency depends on the speed, the angular speed of the rotor. Uh, the angular speed is a function of the slip according to this formula. If the slip here is 1, this means the the rotor is in standstill, is stationary. Then the frequency is going to be F. But if the rotor speed up, if the rotor speed build up, then we are going to have different frequency. The frequency will be less. So how about that? We move this S out of the bracket. So we end up with this formula here. So we have a formula like this, and we define this expression as XR0, where XR0 stands for the reactant at standstill. So now we have a lot of important information here, and we don't have enough space. We are going to remove something to free up some space. The So according to what we have got here, the current will be given by the bottom expression of the current is going to be R plus J times S X R0. So now you have this circuit running at a reduced frequency, and this reduced frequency depends on the speed. So can you normalize this circuit? Normalize it so that it becomes almost independent of the angular speed. So we are trying to come up with a circuit, a new circuit for the rotor. And this circuit is running, is normalized to frequency F. We can do that. What we can do is, right, we have this expression. We divide the top and bottom by S. So we have this new expression here. So with this in mind, the top expression stands for the voltage. Then the voltage itself can be expressed. So we can express this expression uh, as another circuit. So the voltage here, sorry, right, it should be the voltage. The voltage here, yeah, maybe we can. The voltage here now is the voltage at standstill. And the inductance here is going to be the reactant at standstill. together with an resistance. But this time the resistance is going to be R divided by S. So now we have already transformed the circuit. Originally, the circuit is running at frequency SF, but in this time we are now replacing the circuit with the rotor running at a standstill. This means there is no velocity. So the stator and the rotors are both stationary. So in this case, the frequency here is F. So in other words, the rotor itself, if we can do that, then both circuits will be running at frequency F. So now we just need to do some adjustment. And this one is going to be ER0. And the rotor resistance is, so now we are now closer to the reality. Yeah, we have a model, and the model has shown that the rotor itself is stationary, and stands still. And in this case, the voltage and the reactant can be included in the circuit, the transformer circuit. But the resistance itself is the dependent on the angular speed, the slip. So we have the new circuit here, but then we also need to be careful. This is a transformer circuit. We don't have all the parameters. We only need we only have the conceptual picture of the rotor, and of course, where we have good enough understanding of the stator. So what we need to do now is to further simplify the transformer circuits here. The rotor of the induction motor have low wire connection, and you cannot measure the rotor resistance, and you cannot measure the rotor reactance. Of course, right, it's impossible to know rotor the rotor EMF. But then it doesn't mean that we cannot continue to build a model. So right now we have all these parameters. We can come up with a model with the same stator, same harmony. And we have V1 here. XM. So nothing is going to change in the stator. But we are going to, this time we are going to lump everything. We are going to refer all the parasitic in the secondary, in the rotor, to the primary. This is the way how we model the transformer anyway. If we can do it for the transformer, we can equally do it for the induction motor. So let's do it. And we use JX2 to stand for the referred secondary reactant. And of course, we have a resistance here. The resistance is going to be R2 over S, and the slip is not going to change. And in this case, the voltage here is going to be ES. And now we have to write down the relations here. The Let's say the turn ratio. We just imagine there is a turn ratio here. The turn ratio is going to be A equals to ES divided by E R0. So I better write down in somewhere. So A is the turn ratio, and ES divided by ER0. And if you have a current here, I2, I2, you should say dash, right? I2 dash is the referred current. Originally, the current here is IR, so IR divided by A. And the voltage here is the voltage here is ES, right? Is going to be AER0, okay? And then the rotor impedance is going to be A square times R. And then the rotor reactant, A square, and then X R0. So with this in mind, we have also we have got a list of parameters. But normally, these parameters are given in the examinations. So this is the model of induction motor, and from now onwards, we don't really need the diagram here, because all the parameter has got lumped to the all the parameter in the rotor has been referred to the primary, and we can erase this diagram. So this is the the model of induction motor, and you can use this model to model everything, including the power. Now, talking about the power, and we can model the power meaningfully using this diagram. As, as I have already emphasized, here, from here to here is stationary. Sorry, from here to here belongs to the stator. So including so the status actually everything on the left of the red curve or the red line here is the stator. And everything on the right of the red line here belongs to the rotor. So let's make it clear. And we have got all these parameters here. And let's write down the parameter in this space here. A is equal to ES divided by R0, and I2 is equal to the rotor current divided by A. And then the rotor resistance R2 is equal to A square R. And then the rotor reactance is here. A square and then X R. Okay? So we free up a lot of space now. Now, first of all, this circuit can be meaningfully used to model the power, the torque, and even the torque speed characteristic. First of all, we have a resistance here, and this resistance is due to the stator winding loss. And we also have, let's write this down first. R1 used to be used to model the status winding loss. So the status winding loss is I1 square times R1. And this power is for one phase only. And we have three phase. So the whole expression has to be multiplied by 3. And the power input to the motor can be modeled as the voltage times the current. And let's say, right, the power input here is going to be PLCL copper loss and 1. And this one is going to be, P in. Is going to be the voltage times the conjugate of current. You need to put 3 here. Or B times the conjugate of voltage times current. And now we have to use a symbol for the winding loss, right? Say the winding loss is EL, PCL 1. 1 stands for the stator. Is equal to I1 square and then R1. The core loss is due to the eddy current. And again, we can model it. The core loss is going to be PFE. Yeah, this means the metal, the ferromagnetic material is equals to the voltage here. The voltage here is actually ES. So 3 ES, the absolute value of ES divided by RC. So this is the so-called core loss. Now, as I said, everything on the left of the stator sorry, everything on the left of the red line here belongs to the stator. Right now, we have already modeled the loss, the winding loss for the stator, and the core loss of the stator. So essentially, we have already taken care of all the losses in the stator. And the power input here include everything. Uh, include the power for the status and include the power for the rotor. So what is the power for the rotor? And on the right side of the red line here, the red dashed line, and we have only one element that can be modeled as a loss. This is the R2 dash divided by S, the referred rotor loss, the referred rotor resistance divided by S. And this one is the rotor power. And we have a name for the rotor power. And let's write this down. We don't need this at the moment. The rotor power is called air gap power. And it is PAG, air gap power. And according to the diagram here, the circuit diagram, right, have I2 and this one, the, the air gap power is going to be the magnitude of the secondary current. So I2 dash square times the resistance. The resistance is R2 dash divided by S. So with this in mind, we can continue to model the circuit. The winding loss, if we have the winding loss for the stator, we should equally have the winding loss for the rotor. So the winding loss, the rotor's winding loss is say right, we have a P C L, we have a 2 for the rotor. And then again, right, we can do this. I2, according to this formula, we can equally do this for this rotor. R2, and then dash. The rotor power is a combination of the winding loss and also the converter power. Converted means the power that has been converted into mechanical power. For the time being, let's forget the friction. And we have the power here, and we have the air gap power, which is all the power belonging to the rotor. And we also have the winding loss here. So it's fair to assume that the convert power P cons is equal to the all the power belongs to the rotor, say PAG minus the winding loss. So according to the equation here, we have this expression, V I 2 dash, and then R2 dash, and then the winding loss here is according to this formula, R2 dash. So if you work out carefully, this expression is going to be equals to PAG, the air gap power, times 1 minus S, 1 minus the slip. So this is the reality of the induction motor. So let's write down the important conclusion here. We have this and that, we have almost everything. And what we don't have is the torque. And we are going to calculate the torque in the next video. Right now, for now, we have already got enough information. We have got the model for the induction motor. The model is based on the transformer model. And the only difference between the transformer and induction motor lies in the rotor. In the rotor, the uh, the impedance is dependent on the angular velocity, uh, which in turn depends on the slip. But the transformer doesn't have uh, this issue. So if you have any question, feel free to leave your questions to the comments box underneath the video. For now, well, thank you very much for your support. So see you next time.